can you guys see my iPad?
Yeah.
All right, great. So um, this is for Yuya and also for people watching this lecture. So what we're going to do today is that we'll start from the fundamental topics in graphs. So like a brief introduction into graphs, how it's represented, what are the types of graphs, and what are the graph algorithms. And then we'll cover problem 1 and 2. And if we have time, we'll cover Kruskal's algorithm in question 3, as well as this topic called minimum spanning tree. Also, just to do a poll, Evina, have you watched the lecture on graphs so far?
I haven't.
It's okay, because I don't because neither has Shafali. So today, what's great is that basically everyone's at the same level of understanding in terms of graphs. So I can do a cover that's not like biased.
Okay.
And I felt that it was great. Okay, so first of all, sorry?
No, I said it's okay. Yeah.
Yeah. Okay, so first of all, have you guys heard of graphs before?
Well, yeah, because the homework.
So just to remind you guys, trees are actually graphs as well. So all the binary search trees that you guys have learned so far, and like heap and stuff, those can all be considered as graphs. Sorry, maybe not binary, maybe not heap, depending on how it's implemented. But binary search tree is definitely like a sort of graph. So a graph is a way. So basically, a graph is a way that we represent data and the relationships between data. So what I mean by that, so think about, so there are two important, I won't say properties, but there are two important components of a graph. One is called the nodes, which are also called vertices. So the vertices and nodes, you can think about it as like nodes in a binary search tree. They sort of, sorry, was there anything wrong?
No.
Oh, okay.
Wait, is my speaker, like, is there anything wrong with it? I'll try it with my AirPods.
Yeah, I'm hearing sounds. Maybe it's because of the echoing sound. Yeah.
I'll just connect through AirPods.
No worries. So nodes and vertices are where we store data. So in the case of binary search tree, if you have a bunch of integers, then you'll have each node containing one integer. And once you get to a specific node, you can extract the data, right? And the edges, which are just lines like these, the edges are components that sort of represent the relationship between data. So what is why do we care about graphs, and why is it important? So the motivation is as such. So imagine you're a governor in California, right? And you want to figure out what is the fastest way to travel in between cities. So say maybe from Cupertino to Sacramento, or from I don't know, Berkeley to LA. Then a way that you can do this searching is that you represent each city, so each of the locations, as a node or vertices in a graph, and their distance, so their corresponding distance, as like the edges. So maybe something like city A and city B, and say their distance is 100 miles, and this will be a simple graph like this. Oh, okay. So, and as you can imagine, the graphs are very convenient because it allows you to represent like very complicated data and relationship, right? So think about this graph. If this is a representation of a map, then it is really storing like a lot of relative distances in between each locations, and also like just a lot of cities are being represented. So this represents relationship in the graph. So is that clear so far?
Yeah.
All right, great. So I want to talk about the representation of graphs as well. So I'll give you guys a quick check. Do you guys remember how binary search tree is represented in code? So if you have ever seen like assignments of binary search tree, basically you have a class. I'm just gonna write pseudocode. That's like BST. And in between this class, you have some fields, maybe like say size. And then you have a node that's called left subtree, and a node that's called right subtree, right? Do you guys remember that?
Yeah.
And a node is like a class within the BST class, right? So what's great with this representation is that you basically only care about the nodes, right? Because the thing with BST is that you know that a node either has one child or two children, right? And it's always gonna have like a parent, except for the root node. So what I'm saying is you can think of a binary search tree as a data structure where the relationships are rather fixed, right? So it's always gonna be sort of this type of structure, and there's not gonna be exception. But what is more complicated about graph is that, say you're representing a city, right? You really can't tell if the two, if in between two edges, two vertices or nodes, there is like an edge until you actually check it, right? So with that being said, we sort of need like a more flexible way of representing graphs. So there are two representations that are very popular. One is called adjacency matrix. So I know Evina has taken Math 54, but what about you, Shafal? Have you taken like a linear algebra class so far?
I've taken EE,
Ah,
like
great.
16A, and I'm doing 16B.
Okay, yeah. Then you know what a matrix is. Great.
Mhm.
So in a matrix, in an adjacency matrix, how do we represent a graph? So suppose I have a toy graph that has two edges and three vertices, right? So an adjacency matrix is that all the column and row labels are the names of the matrix. So something like this. 1, 2, 3. So these are the nodes or vertices, right? And also for the row labels, there are also the name of the vertices. And then so what does each box mean? So this box means from node 1 to node 2, is there an edge? So I'm gonna introduce what's a directed graph and what's a undirected graph later. But right now, as you can see, there is like a edge in between node 1 and node 2, right? So this is gonna be a 1. So 1 represents that there is an edge, and 0 represents that there is no edge. So can anyone tell me what's the corresponding number for this blank and this blank? What number should I put in
0.
for both of them?
Yeah.
Yeah, exactly. Because there is no edge from 1 to 1. There's not a self-containing edge, and there's also no edge in between these two. So in an adjacency list, we're just in an adjacency matrix, we're just representing the existence of edges with a bunch of ones and zeros. So 2 to 1, there is an edge. 2 to 2, nope. 1 to 3, yes. 1 is okay, 2 to 3, no. Yeah, cool. So but there are also, so this is what we call a undirected graph. That means that there is no direction for the edges, right? So what's a directed graph? So types of graphs, undirected and directed. So a directed graph will just be, say I have the edge from 2 to 1, right? Then it's gonna be a sort of like an arrow that points towards 1. And if I have an edge from 3 to 1, it's also gonna be an arrow pointing towards that. But notice that there is no edge from 1 to 2, right? So that means like if you so imagine you start from 2, you wanna travel to 1, but you cannot travel back to 2. So that's the difference. Whereas in undirected graphs, traversals or like movement is like bidirections. So a very good example of directed graph is, do you guys know the those one-way routes on the south side of campus?
Wait, one-way route?
So basically, remember in the south, at the south side of campus, there are some roads that you can only travel like one direction, so you cannot travel backwards.
Oh yeah,
Either
Yeah.
from west to east or east to west.
Yeah.
yeah.
So say you travel from Cafe 3 to say Chipotle, right? There's only one direction that you can go.
Mhm.
You cannot so you cannot follow the original route back in the reverse direction. So why might directed graph be useful other than say, roads and locations? So imagine you want to construct a social network that represents how people know each other, right? So if I have a node, say Obama, and I have myself, right? And an edge is represented such that if one person knows the other. So which direction do you guys think the edge should go?
It goes down.
It goes up because
It goes up.
I know Barack Obama, but he does not know.
You know. Oh yeah.
Yeah. Right.
Okay.
Yeah, but say if two people know each other, right? So say President Bush, then what you're gonna see is you're gonna have actually two edges between nodes, right? Where one goes to the other and the other one goes back to the original.
Mm.
So, there are a lot of other ways such that a directed graph is useful, but one very good way of thinking about it is, social networks. Another example that you guys might be familiar with is, say, links in between website, right? So if I have a hyperlink from one website to another, then that represents a directed edge from that website to the next website. But in that website, there might not be a link that goes back to the original website. So yeah, those are examples. So in the case of adjacency lists, realize something very important here. For undirected graph, this adjacency list is actually a symmetric matrix, right? So if you were to write it in matrix, it looks like this. And this is actually symmetric, right? If you just take a look.
Mhm.
That means that the transpose of this matrix is the same as the matrix itself. But that is because in an undirected graph, if you have a edge from one node to another, then of course from the other node back to yourself, there's also an edge because undirected graphs doesn't count for direction. But notice that in a directed graph, what you can have is there might not necessarily be the case, right? So in an undirected graph, your adjacency matrix is also symmetric, and in directed graph, that might not be true. Okay. So another way we represent it is called a edge list, or AKA adjacency list. So not a matrix, but a list. Yeah, so what do I mean by that? So in an edge list representation or adjacency list representation, you have like a list for all the nodes, right? So again, in this example, you have a list for 1 where sort of all the elements in the list is like the nodes you can reach from 1. So you see that there's the outgoing edge from 1 to 2 and 3. So you'll put 2 and 3 here. Whereas for the list for 2, there's only 1 edge from 2 to 1. So it's only gonna be 1. And for the list of 3, it's also gonna be 1, right? So this is what we call the edge list. So to find if an edge exists, you first go to a specific node, and then you traverse all the elements in this list to see if that edge that you're looking for actually exists. Okay, so now I want to talk about some very deep conceptual understanding of these two representations. Here's the question for you guys. For these two representations, which one would seem to be more useful for a graph? Just in general, which one takes up, say, less space?
The list.
Okay, why do you think that is the case?
Because like you say, like take up like less space, so that's why like I feel like in terms of space, like list would be like less complex compared to matrix.
I see. That is a very good observation. So remember in the matrix, whether a graph exists or not, we'll have to sort of still write them out, right? So we're essentially writing out all the possible edges in a graph. So what I mean by that is, if you have 1, 2, 3, all the way to n vertices, then what's the size of your adjacency matrix? So think about it. For each, yeah. Do you have an answer?
N squared?
Yeah, you're actually gonna need to write out n squared edges, right? So what's the downside of this? Since whether a possible edge exists or not, we're still writing it out. So we're still representing it as 0 or 1. So imagine if we're storing a graph that has a lot of vertices but not so many edges. So here's an example. Say, let me think about a good example. Okay, say you're at a frat party, right? And you're thinking of meeting some new friends. Then you'll probably imagine that in this party, which you are meant to be introduced to new people, you probably don't know most of them, right? So if we were to represent it with a graph of social network, what would that be like? So imagine we are the 3 poor people in this, imagine we're the 3 poor dudes in this party. Then all the other vertices we have, right? There's probably not gonna be any edge to any of those because we don't know any of them, right? Well, but in that case, we still need to write out all like the representation of these edges, whether they exist or not in this matrix, right? So in that case, if we were to represent a graph with many vertices, so many nodes, but very few edges, then we're wasting a lot of space. So in this case, Ivina is correct that a edge list will be a more efficient way of storing a graph. But let's consider another case where you have very few vertices, but lots of edges. In this case, which one will actually be more efficient? This is a trick question. Think about access time. Here's a hint. Also, for an adjacency matrix, you can think of it as like a 2D array.
Would it be the matrix?
Yes. And why do you think that's the case?
Because you can index into like which array versus the list. You have to iterate through all of them.
Yeah, exactly. So imagine you have lots and lots of edges, right? although it's the same amount of information you're storing in an edge list and a matrix, but when you actually want to check if an edge exists, right? So say if I want to check if an edge between A and B exists, right? All I need to do is just to take the corresponding index of A and B and pass that into the 2D array, right? The access time is going to be constant. Whereas in the case of edge list, I'll need to go to the list of A, and then I'll have to go through all the edges A has, right? And in a graph where we have very few vertices but lots of edges, A is going to have like a bunch of edges going out, right? So in that case, actually the adjacency matrix is more efficient. So going back to our question, which representation is more efficient? The answer is that it depends, right? So I won't give you like the precise like number. So there's actually like a cutting point where if the number of edges is above this number, matrix will be better. Otherwise, it's like the edge list, because I don't think this is like 170 concept. But just remember that you might be asked like these type of conceptual questions on the exam in terms of like representation. So yeah, cool. So I also want to talk about types of graphs now. So remember, for types of graphs, we have directed and undirected graphs, right? There's another way to sort of divide the graphs. You can either go by cyclic and acyclic. So what do I mean by cyclic and acyclic? It means that if a graph has a cycle, it's called a cyclic graph. And if the graph doesn't have a cycle, it's called an acyclic graph. So here's an example. Okay, is this graph a cyclic graph or an acyclic graph? What do you guys think?
Acyclic?
The answer is actually it's cyclic.
Oh.
But why? It's because there's a cycle here.
What about the last one?
Oh yeah, the thing is, the graph itself doesn't have to be one big cycle, but as long as it has like a cycle.
Oh, contains a cycle.
Yeah. Sorry, I
got
should have made it more clear. Yeah, but if a graph contains a cycle, then it is a cyclic graph. So I'll give you guys a precise definition of cycle. A cycle is a path such that without repeated nodes, you can traverse, that means move, from one node back to itself. So what is a path? A path is just a sequence of nodes and edges such that allows you to move from one node to another, right? So look at, for this graph, a path will be from E to B to B, from B to D, and from D to C. That is a path from node E to node C. So a cycle is such that you can go from one node back to itself, so from E back to itself, without every repeated node. So what do I mean by that? So E to B, B to D, D to C, C to E. But you don't count this E edge, you don't count this E node twice, because that is the last node that you reach. So I'm saying all the nodes in between this path is not repeated. So if you have something, say, if you do something like this, E to B, B to D, D to C, C to A, and back to C, and then to E, then that will not be a definition of like a cycle. Even though there is a cycle in between, but this particular specific path is not a cycle. But if you get rid of this traversal and only leave it with that, that is a cycle. Don't worry too much about the detail. I don't think you actually need to remember the precise definition of a cycle, but as long as you know, like it's sort of like a circle where you can go around. That's good enough for 61B. Yeah. So any questions on cycles?
No.
Okay, now here's another question that's very important, I think, conceptually. So is a tree, previously I said a tree is a graph, right? Is this cyclic or acyclic? A tree.
Acyclic.
Acyclic.
Yes, because the definition of, one of the definition of a tree is that it contains no cycle. You'll learn about this in CS 70, but yeah. So a very good example of an acyclic graph is a tree. All right, great. So I think that's all I have to cover about graphs. Is there any other questions that you guys have? It's actually a very big topic, so it took us a lot of time. Okay, cool. So now I want to talk about DFS, BFS traversals. So since you have a graph, right, you probably want to search for like potential paths in this graph. So remember the example where you are the governor of California and you want to figure out like the shortest path in between cities, right? So you want an algorithm such that from one location, you can retrieve like the shortest path to another location. So this is where sort of graph algorithms are introduced. So why are they important? Because they allow you to search for potential routes and paths within a graph from one node to another. So there are a lot of different famous algorithms. And first one is called DFS. It stands for depth first search. So what's the characteristic of depth first search? So I'm not going to talk about the pseudocodes yet. So I'm not going to talk about how you actually implement it. But the idea is that you start from a node, you pick one of your neighboring nodes, and you go along that direction. And now you're at a different node, right? And then you pick another one. As long as at your current node, you still have a child, then you keep going. So at D, right, I have B and F as my neighbor. So I go again to B and then to E. But whenever you reach a node with no neighbors other than like the place where you came from, then you traverse back until you're yet again at the condition where you have an unexplored neighbor. So here's an important fact about DFS. Whenever you visit a node, you mark them as visited, so that you don't revisit them again. And once you reach here, D, right, you'll see that F is unvisited. So you'll keep going until you reach your destination. So say I want to find a route from H to G, right? Then at this point, I know that I found G, so that I will stop there. So what is like the great thing about this? So you can sort of imagine, right? If you're in a tree, say just a binary search, binary tree, right? Like this. Then a good thing about this is that it's actually gonna give you like one very deep. So say if you want to find like a leaf node in this tree, right? The property of this DFS is that as long as there is like a neighboring node that is unvisited, it's gonna keep going along the direction. That means that it's in the fastest time it's gonna reach the bottom of any tree. Because imagine yourself from here. No matter what route you take, you never visit any node on the same level twice because you are always going like to your unvisited neighbor. So you'll be able to reach the maximum depth of any graph or tree in the shortest amount of time. So so that's the reason why it's called depth first, because you are going for a depth. So any question on the concept of DFS?
No.
Okay, so now I want to talk about how it's implemented. And I think a good example, so there's, so let me just show you guys like what Professor Hilfinger has on his slide. So could you guys see my computer screen?
Yes.
Yes.
Okay, so I want, okay, maybe what Professor Hilfinger has is, oh yeah, here it is. So you start, your input is a graph and your node is your starting place. So if your current node, that means your starting place, is not visited, you first mark it as visit and then you visit this node. So that means like you sort of check if this is like your destination, right? And then once you've visited the node, you're gonna check all your edges. That means you're gonna see all your neighbors and you're gonna traverse them, right? But remember, for a already visited node, this condition, so imagine you have a recursive call on one of the already visited neighbors, right? And then say W, you already visited W. So in this statement, this if condition is actually gonna block you from revisiting it. So then you're only gonna visit like neighbors that you've already seen, you haven't seen so far. Yeah. So this is like a rough idea. I also want to, there's also a very good pseudocode, let's see, in my 170 textbook that I think is even more concise. So here is another pseudocode. So you start, so for DFS, first you create, say, an array of Boolean values where you mark the status of whether a node is visited or not, and you initialize it as all false. So that means you haven't visited any of the node in the graph. And then for unvisited node, you explore it. And the explore operation is what Professor Hilfinger wrote. So this is essentially the same. Yeah. But there's one very, very important key point about this algorithm that I want to talk about later. But let's walk through a problem now. Okay, where's my slide? Ah, awesome. So question 1, for the graph below, write the order in which vertices are visited using specific algorithms starting from A. Break types by alphabetical order. That means, like, say you're at D, right? And if you have C and F on both unvisited, so forget about these numbers now. Then you're gonna visit C first because alphabetically C comes to first. Yeah. So this is gonna be DFS. So you're starting from A and you wanna visit the entire graph, right? So a very important thing is that whenever you reach a point and you wanna check all its neighbor, there's a place that we actually store its neighbor. In DFS, we call it stack. So a stack, are you guys familiar with a stack, by the way?
Yeah.
Yeah.
I think before midterm it was like, yeah.
Oh yeah, so you guys know the difference between stack and queues, right?
Wait,
Yeah.
which one is the little one and which one is the? Wait, Prince, you muted yourself. Prince, you muted yourself.
Am I back now?
Yeah.
Sorry, I think what was going on is that my audio went wrong. Like once in a while, my audio breaks. Let me reshare my screen. Wait, so where was I cut when I was speaking?
At the beginning, like after you asked the question.
Okay, cool. Well, I think Ivina mentioned LIFO and FIFO, right?
Yeah.
So
Stack
FIFO
is the little one, right? No, go ahead. Sorry.
Yeah, stack is a LIFO one. That means last in, first out. So think about a stack of toilet paper, right? Like the most precious good we have in times of trouble. So what is the stack of toilet paper? It means that you're stacking them up like one on the other, right? Until you have like a tower of toilet paper. So last in first out means if you have something that's like that enters the stack at last, it's gonna be on the top of this stack, right? So whenever you remove, you take off the thing on the top. So that's why the last thing that enters the stack goes out first, because you're taking them out. And FIFO is like a queue. So a queue is like where you actually line up and stuff and be disciplined. So if you stay in the queue the first, then you're gonna leave the first, right? So imagine you're buying boba and stuff. So that's why for a queue, it's first in, first out. So what's important about DFS is that whenever you visit one node and you have like all its neighbors, you're gonna sort them in the stack. And I'll explain later why that's important. But okay, so now you have two elements in a stack. So which one do you go next? C or G? Remember, we break by alphabetical order.
C.
Yeah, because C comes first. Cool. Now we have G, H, and D in stack, right? Where H and D enters the stack at the same time. But okay, so which one are we going next?
D.
D.
Great. So now which node next?
B.
B. Exactly. And then?
E.
Cool. And then?
F.
F, G, H.
H.
Right? But okay, so now I want to go back to why using a stack is important. So realize that the earlier neighbors of your visitor nodes, right? So at the very beginning you have C and G, right? But because you're always gonna go along one direction until you hit like a wall or until you have no way to go, and then you're gonna go back to the most recent place or node where you actually have like another unvisited neighbor, right? So the property of stack where the elements that enters first comes out last means that the earlier encounters of neighbors, such as this G, will not be popped out of the stack until like the very last. So until like you've visited all the others. So if you just look at how the stack changes here, it's always the most recent neighbors that goes on the top of the stack, right? And that gets pop out first. So that guarantees the sort of property of depth first search where you're chasing one depth specifically. This might sound abstract, but do you guys have any question about using a stack?
I think I'm okay.
Yeah,
Okay.
me too.
Maybe once I introduce a BFS example, it'll be more clear. Okay, so I want to talk about BFS now. So the operation of BFS is exactly the same as DFS. So you can write a code where everything is the same, except for where you store the neighbors. So instead of using a stack, we'll use a queue now. So let's walk through this with. So I'm gonna walk through this with you guys to sort of show you what's the difference. So, but I want to first talk about maybe the concept of BFS. So the property of BFS is that you're always gonna visit your closest neighbors before you visit some other neighbors. So a good example will be, I want to draw it actually. Can I let's see if I can redo my screen. Can you guys read out my meeting ID since I can't see it in share mode? Oh wait, I think I found it. Never mind.
Okay.
Have you guys ever heard of BFS before?
Yeah, didn't we do it with like binary trees?
Yeah.
Oh great. Then yeah, hopefully this is gonna take up less time. So a very good way to visualize the difference between oh wait. I think, am I sharing or not?
I didn't see it.
No.
Oh, I see it right now.
Okay, so a very good way to visualize this is think about a graph that looks like a spider net or like a thing that grows outward. It's kind of ugly, but for time's sake. Sorry. Okay, so what DFS is gonna do is that it's gonna go along one direction before hitting like a node where you have no unvisited neighbors, right? So imagine you start from here. DFS is gonna go all the way to one of the along one of the path here, right? Whereas the DFS, it's gonna first you're gonna start and you're gonna visit all your closest nodes. So it's gonna visit the entire this entire circle, and then it's gonna visit all the nodes that's like next closest to you. So you can sort of think of it as the visiting order depends on the number of edges the current node is from the original starting node. It helps us. Wait, did I go cut off again?
Yeah, you
No.
did, but now you're back.
Yeah, you're back right now.
Okay, so a very good thing about BFS is that it allows us to find the closest path to a node, because many of these nodes, it's not gonna like the order of visit. So you first visit all the closest neighbors, right? And then you visit the so you make sure that you're visiting them by distance, right? Or sort of number of edges away from the original node. So for any node that you visit, you're not doing some extra work where you're traversing like all the way here until you like hit like DFS, but rather you are visiting them by like the increasing number of edges. Okay, so for time's sake, let me go back to my example on the slides. So we're gonna start with a queue, and we first put C and G. And what's the next? So for a queue, the first element's gonna be pop off, right? So we're gonna visit C, and then we add D and H. But because this is a queue, we actually wanna put like the we actually wanna pop like the things that enter first. So now instead of popping D, remember in the original DFS, we're popping off G. You guys notice something about the relative distance? Sorry, not distance. The number of edges between C and G. It's both one edge, right? And
Yeah.
visit D and visit H. And D and H are always two edges away from A, right?
Yeah.
And then F is also two edges away from A, right? And then we visit B, which is 1, 2, 3, 3 edges away, and E, 4 edges away. So what this means is that any path you found alone, this visiting, it's always like the shortest number of edge you can reach from one node to another. So that's why it's called breadth first. You want to be as broad as you can on visiting all the edges that's closest to you before you move on. Yeah, so I think we're this is just about time. But any questions on BFS and DFS?
So does that mean the order of a BFS can be slightly different?
Than DFS or
does it have to go in alphabetical order like ACG? Could it be AGC?
So usually when you have like two neighboring nodes that's like off the same number of edges away from you, the question is going to specify how you break ties. Okay. So it's always going to be depending on how you break ties. Yeah. So even DFS can be different, right? So if I say I want to break tie in DFS with reverse alphabetical order, then instead of visiting D, I'm actually going to visit H first, right? And that's going to be a different order of visiting. Yeah. So any other questions?
I see him good.
Yeah, me too.
So unfortunately, I don't have enough time to go through question 2, but I think DFS and BFS are the most important topic in this class. And if you guys like, I can do a
You're muted again. Prince? You were muted.
yeah.
Oh,
Am I back?
yeah.
Oh shoot. Okay. So so for Dijkstra, if you guys are interested, you can either
Prince, I think you got muted again.
and okay, this is did I get cut off again?
Yeah.
Hello?
Yeah, we can hear you now.
Wait, can you hear me?
Oh, okay, I'm back. Cool, great. So okay, anyways, thank you guys for coming, and I'll see you guys next week.
Okay,
Okay,
thank you,
thank
Sorry for the
Prince.
poor
you.
audio I have.
Thank you so much.
Thank
Bye.
you.
I think I think I can't hear you guys. Like something else broke, but I'll try to fix it. But yeah, bye guys.